All right, welcome back, everybody. Today we're going to continue on. I ran to Safeway at lunch today, and if you didn't notice, the roads are slick. So slick, in fact, that I swerved on the corner. Whoa, whoa.
That was
Cool.
the best thing I've heard in my life.
World star. All right. What's up? Yeah. I have one right in my hand. Please don't feel it. Cool. So, this is what we were talking about yesterday. And before I show the name, what is this? So this is the primary coil of a what?
A transformer.
This is a transformer. Thank you again. Now, looking at this, these things do one of two different things. All that these do is allow us to push the voltage way up and then to lower it back down. Before we continue on, just a quick kind of recall. Why on earth would you ever want to push the voltage way up high?
To travel far places.
To travel. That's the big deal. We need to make sure that we're pushing harder to make sure the energy and the electricity travels all the way through that conductor, whatever it is. There's some resistance we got to push. Okay, now as we're looking at this, this is where we left off, and I spent a lot of time really specifically drawing it, and I did so for a particular reason. What we have coming into this is 300 volts. That's the current that pushed through this now solenoid, right? Okay, so just a quick reminder, I run a bunch of current through that coil on the left, and whatever the amount of current was, it's pushed by 300 volts. When current passes through that and it's alternating, what does that big piece of metal become?
Magnet.
A magnet. Now, the fact that that current is alternating means what's happening between the north and south pole of that magnet? It keeps switching and switching and switching. Now, the basic idea here is the whole piece of metal becomes a magnet, right? Are you guys okay with that?
Yeah.
Like, it's like what we did, but the nail's just bigger. Okay. Which means, is it still a magnet over here?
Yeah.
And is the magnetic field still doing this over here?
Yeah.
Okay. Are there electrons in here, just in general? And when I do this, what do they start doing? They start wiggling, and they start moving, all the same. And when you have wiggling or moving electrons, you now just get electricity here, right?
Yeah.
Okay. Now, what winds up happening is we see this electric current kind of get transferred between the ends of this magnet. Okay. We'll look at a better visualization here in just a second, but that's the basic thing that's going on. On this side, we have our primary coil, and I'm trying to remember the notation that we're going to write it down with. Does everybody have this picture? Okay. Over here, we have our secondary coil. Now, depending on where you look with this, you might see this as coil 1 and coil 2, or primary and secondary. Either way, I'm good with this. If we want to call this the primary voltage, I would just call this VP for voltage that is P for what? Primary. What do you think we should use for the voltage out? VS for secondary, absolutely. Now, I'm going to show you guys a relationship here, and I want to see if maybe, just maybe, we can reason out what it is. Now, I'm looking at this, and without any additional knowledge, I just want your gut feeling. This transformer that we have on the board does one of two things. It either steps up or it steps down. Those are the only options. Okay, no discussion, just pure gut feeling. Hands up if you think this is a step up.
Yeah.
Okay, so 4 or 5 of you guys said step up. Everybody else thinks step down, or you're just abstaining because you're not sure. So that's fair. Let's think about, I'm trying to think of just being able to intuitively get this out. Which one has more electrons, the one on the left or the one on the right?
Right.
Why? You're right, I would agree with you. More coils. There's physically more space to hold electrons. You guys cool with that? Okay, so this is a step up, just so you guys know. This is, in fact, a step up. How many more coils does the right one have?
3.
3 more. How about if I compared, like, the ratio of new to old? It doubled the coil, right?
Yeah.
Okay, gut feeling. This is a step up, and I doubled the coils. Any gut feeling what's going to happen with the voltage? It's going to double. We get 600 volts out of this. It does exactly that. Now, this feels, when you first see it, like maybe we're breaking the rules of physics. Because what can we never create nor destroy? Can't do it. What does it look like we just did? Looks like we created it. Now, we didn't, and it's easy to make that misconception. I know that the voltage increased, and it doubled. In tandem with that, we don't see it on this picture, but any guess on what happens with the current? It can't double as well. Then we would really, really, truly be cheating. If one thing doubled, the other thing must do what to stay the same in the end? Cut in half. We now just have half the current. There's no energy created. There's no energy destroyed. It's the same when you take the electric power, which is voltage times current. Same power in, same power out. No rules are broken here. We just don't get to see it. Now, I should probably get my notes so I don't miswrite something here. This is a what coil? Or sorry, transformer? Step up. And you can tell very clearly up because what stepped up? The voltage literally steps up from in to out. Okay, so this one, just to make sure we can label it, we'll just go ahead and above, we'll call this step up. Now, we're also going to draw a picture of a step down, and we have a couple routes. Do you want to do the exact same one? Do you want it to look more realistic?
Cooler.
Exact same? I'm fine with that. So, what I want you guys to do is, one, is kind of annoying, and they don't really have these small numbers, but you need to count your coils. Like, however many turns you're making around this, we need to actually count it so we can make this be a true step down and calculate it out. So, I'll set it up as a basic step down transformer real quick. So here's our lovely, what will become our electromagnet once we run, current through it or around it. I'm going to move that over. I should have copied this twice yesterday. All right. Now, I'm going to make you guys draw this. I want to check something here. Here's what I'm going to give you. On this one, I'm going to move that. That looks like verses, like these guys are going to fight. Like maybe they would. That's not what's happening. Weird that line just disappeared. Yep, I'm going to move that out of the way. This is the voltage VS for secondary. Okay. So if I just put some lines here just to say, look, we're separating it. We still have a primary coil. And then let's say this time, I'm not going to specify, but how many volts do we want to put into this? 100? So the in voltage is 100. Cool. You're going to draw your coils here in a second, but I'm going to ask you to think this part out. Do what?
One coil. So let's just.
I don't know. What's the out voltage? What do we want to take it down to? 50?
Wait, can you do half of it?
Sure. Let's do 50. I'm fine with that. 50 volts out. I want you guys to determine the number of coils that would work here. You're going to draw a step down. Now to step up, more coils on the left or right? You need more on the side that it comes out of, right? If you're stepping down, should you have more on the left or the right? Left. Cool. I don't care how many coils you pick. Don't make it like, just don't randomly do it. I need an actual number. Cool. I'm going to give you guys a second. I'll come around. If you have no idea what you're doing right now, could you ask me? Bet, bruz. Cool. And look at that. We now have a step. Whoa. What happened there? Weird. No idea. All I do know is that we just have a step-down transformer. Now, as we look at these, there is a super-duper nice mathematical relationship here, and I think it's pretty clear. As, like, there's a ratio here. All right. What's the ratio that we're looking at? Does the ratio of the voltage between the in and outside of either transformer relate to the number of coils that we had? Like, they're the same, right? If I were to take 300 to 600, that's 1/2. Or if I did 600 to 300, that's 2. Just depends on the direction I go. Am I losing you guys? If I do 600 divided by 300 with the voltage, what would that be equal to with the wrapping?
2.
Or 6 over 3.
Yeah.
Same 2, right?
Yeah.
Okay, that's a proportion. It just means a fraction equal to a fraction. On this one, if I went number of coils to number of coils, 4 to 2, or if we do new to old, we'll go 2 to 4. That's what fraction? How about 50 to 100? Still 1/2, right? They're the same. They are, in fact, proportional. So what we see here is a result of Faraday's work. And this is, if you're looking around the internet, you're going to see this probably referred to as Faraday's law, at least some of Faraday's laws. Here's the big takeaway from this. So I'm not going to label this. This is called transformer math, but we see it right now. Cool. So check it out. In words, the input voltage Klein, if you're waiting for me to sharpen your pencil, I can talk louder. Over the output voltage. That's just going to be a fraction, right? It's just a decimal or a fraction, whatever you want to think about it. But this is directly related to the number of turns that we have in our coil. So, give me 1 second here. We have input voltage and output voltage. I'm fine with that. Turns in which coil for the input? Which coil, am I going on the primary or the secondary coil for input?
Oh,
Primary. So I'll say turns in primary or input coil, but I'm fine with primary. Over what? What does this have to be over here?
Secondary.
Turns in secondary coil. I hate it. That's not any shorter. I lied. Secondary. That was a weird noise, whoever made it. Not in a bad way. It's interesting noise. No idea what could have possibly made it. Somebody's maybe doing like water drop noise. I don't know.
Is this like energy that like it can't be created or it can't be?
So, Liam asked a question. Is this like energy that can't be created or destroyed? Kind of. We're not creating any energy. Remember, if the voltage steps up, what in turn must come down?
the current.
The current. If the voltage steps down, what do you think goes up on the other side? The current. So you can't increase one without increasing the other. In reality, there's resistance that winds up in here and we wind up losing a little bit. We are working with a perfect or an ideal transformer right now where no additional energy is lost. This is 100% efficient in theory. Now, as we go through this, this is really wordy. Alternatively, what's more commonly used if we look at this is something along the following. VP over VS, which represents what? Primary voltage over the secondary voltage. And that would exactly be equal to, and this one, there's not a like natural choice for this, but I'm going to write NP over VP. Now, only thing that we need, and this looks a little bit different, but it's still a fraction equals a fraction or a proportional relationship. I think we should just make sure that we have this. I don't know if I have to write the V part. What does V represent? Voltage, and VP is what? Primary voltage, and VS is secondary voltage. What do you think N represents? Number of turns in coil. Now, when we say that, that's just what N means, just naturally. That means NP is the number of turns in which coil? Primary. NS then is number of turns in which coil? Secondary. Okay. You guys, I think we've had this conversation. I assume we have. Don't recall, but I would guess you guys are more comfortable with decimals and fractions.
Yeah, I guess.
Maybe not. If not, that's awesome. If so, also awesome. They're both fine. Could I rearrange this if I wanted? Now, I'm not going to go through all the ways to rearrange this. I made a mistake in one little part. I can see it. VP over VS equals NP over... Should that be VP? What should this be? Not PS. NS.
Doesn't that cancel out if there was a
It'd be VP squared.
Oh.
And yeah, we're not going to deal with that. Okay. Seems doable. Seems awful. What's up? It seems awful to you?
I don't know. I just don't get the I don't know.
Okay. So, let's do a problem with these real quick. Easy. Now, when we transmit energy, just so you guys know, like, I don't need to write this down, but we use this when we're sending energy a long way. So we have resistance in wires. We need to get over that somehow. It's by pushing harder, higher voltage. The numbers in real life aren't really 300 and 600. The actual voltage that goes into transformers, like in those boxes over there, is like 100,000 or more. Like scary amounts of energy, which is why they put signs so big that I can tell that it's scary from here, looking across the street. Hundreds of thousands of volts produce crazy big currents, and it turns out crazy small currents can kill you. So crazy big currents can kill you more dead, if that's a thing. Okay.
Are you visibly like able to see the currents?
I mean, if they arc, like, you ever seen a power pole go down? And you probably haven't, but if you see like a power line go down in a storm, oftentimes you get really big, bright blue flashes of electricity. Absolutely, that's a current. You see current when you see lightning. Yep, it's all there. Okay, let's do a quick example. Let's say that we have, can I use all these letters to just represent it? And we're gonna talk it where we're just gonna start right in with our known. Okay, I want you to write down the knowns for me as I speak them. So I'll wait till everybody's there. How much voltage are we gonna pump into this transformer?
600.
600 volts, okay. No, because that's it. Sure, 600. You guys might have already written it. Primary voltage that's going into the transformer from the power plant, 600 volts. I'm good with that. Okay, let's make this a step up transformer. Let's make it a bigger step up transformer. That sounds good. 240,000.
Oh. I would have never.
Cool. We're stepping way up.
4 times?
I think it's like 4,000 times.
Oh, I thought this.
Okay, so we have a big step up, huge step. Hypothetically, let's say that on the, how do I want to do this? Let's say on the number of coils on the primary side, how many?
3.
So we're going to use a more realistic number.
5,000?
We'll split the difference. Let's say it's like 120. What do you think I'm going to ask you to find? I want to know how many coils are on that secondary coil. Cool. We are looking for NS. Now, mathematically, I think everybody in here is probably okay with it, but I totally get that fraction stuff and proportions aren't always easy. I want to set up a proportional relationship. Fraction equals fraction. Now, if I ask what's a numerator and what's a denominator, what's the difference? Which one's on top? Numerator's upstairs, denominator's downstairs. So, my suggestion, and this is going to carry through not just this class, but anytime you're ever solving.
I don't know how I do it.
Too deep. Too deep. All right. That derailed me, but that's okay. Anytime I'm solving a proportion, I would always try to set it up so the thing that we're trying to solve is in the numerator, because it makes it easier. Now, I don't know how your math ability is, but we're about to find out. So check this. I want to set up an equation. Now, luckily, we have that relationship from above. What are we solving for? NS. Should I put it in the numerator or the denominator?
Didn't you say you wanted it?
I would do this if I were you. It's always easier in the numerator. Did I just say you have to? No. It's easier. You can put it wherever you want as long as you follow this order. Vincent, are you sleeping? Okay. As we're looking at it, I'm going to put it in the numerator. NS. And I'm going to write the general equation first. Based on what we have above, that's different than what we wrote, isn't it? Oh, no. Is that okay?
Wait, what?
I'm changing it, right?
Oh, yeah.
But that's okay. How did I change this side of it? I did that, right?
Yeah.
What do you think should happen here then?
It should go to the bottom.
NS over NP is equal to, there's some voltage over here. Which voltage should go on the top?
VS.
VS. And voltage on the bottom? VP. If you're not sure how we made that choice, somebody help. How did I know that those ones had to change too?
Because if one side changes, you get the same thing.
Reciprocal.
Order doesn't matter until, like, however you write your first one is up to you.
Reciprocal.
You're good. Now, I would put an X or an S there is what I would put. Yeah, I just did the reciprocal on both sides. I flipped them both. Okay. Now, I would much rather just solve and then plug in numbers rather than writing 240,000 a bunch of times because that's a lot of writing. What am I solving for? NS. Here's the big moment. How many of you guys see this and automatically think you're going to cross multiply? Nobody does, really? That surprises me. What's a better option than cross multiplying? So don't cross multiply, cross multiply? Is that what you just told me, Sonny?
Oh, I said just do it right across. No,
What do you mean right across? Can you explain?
like straight across. Not like this.
Ooh, that doesn't work.
That doesn't work either. Yeah.
You can't do NS times VS,
No.
because let's look at this. Forget about the right side for now. On this side, I'm trying to solve for NS, but mathematically, what's happening to it? Am I multiplying or dividing?
Dividing.
What am I dividing by?
Yeah.
NP, right?
Don't you gotta multiply that?
So check it out. What's the opposite of division?
Multiplication.
So to undo a divide by NP, we multiply by NP. Now, whatever I do to the left side of the equal sign, I better do to the right side of the equal sign as well. So let's show that math. There's no need to cross multiply. We've set it up with that in the numerator to avoid it. I'm going to multiply the left side by what again? And the second I commit to doing that on the left side, I do it where? To the right side of the equal sign as well. Now, when we do this, you use language that I hate, but that's okay. What happens on the left side of this equation with NP?
It won out.
Ooh, I love that language. Anybody else think that in your head? They won? Everybody else has another word that I hate. They cancel. I'm okay with it because that's what it looks like they do. That sounds like magic, but they gone. What's the only thing that remains on the left side of this equation then? Oh, well that's what we're after, right? Well, let's plug and chug. Cool. NS is equal to, what's VS?
240,000.
240,000. And it's volts over, what's the primary voltage?
600.
600. It's also volts. Now, if you had volts over volts, they'd just divide out, right? The units are gone. Volts divided by volts, or V divided by V, it's just gone. Times, what's NP?
120.
120. Do you think I expect you guys to do this math in your head? Yes, no, just kidding.
Wait.
Is it?
got
I don't know.
I don't know.
4,000 times 120? I don't know.
Wait.
Do it with the calculator. You do not need to do it in your head. If you want to try to do it in your head, that's fine. But I'm going to let somebody calculate it out.
400
It's,
I got it. See, I got it.
What is it? 40.
I scratched my knee.
it's going to be 2,400.
Got it.
I'm pretty sure it's 4,000, isn't it?
28,800,000.
So 24,000 divided by 600.
48,000.
It is 40. It is 40. You were right. Almost 40. We're going to get to 40. 240,000 over 600 is 40. No, it's not. It's 4,000. 400. Oh my gosh.
400 times it by 1.
Okay. I missed a zero. Check it out. I'm doing just first. 240,000 divided by 600. It is 400. I'm now going to multiply that by what?
By 120.
120. So here's my calculator times 120. We get 48,000. Carson, you were right. Okay, big moment of truth. There's no units left. It's 1,000. I just forgot the zero. There's no units, and I'm fine with that. There aren't units, right? Like NP didn't have a units. What is this actually answering? If you just tell me NP is 48,000, so what?
That's
Coils where?
the secondary.
On the secondary side of this transformer, you had to wrap the wire around 48,000 times. Now, that sounds huge, and whether this is realistic or not is beyond the point. The math checks out. You would need 48,000 coils on the right side of this thing to do it. Okay. When we look, yes, sir.
If you if you fill in 48,000 for NS,
Mm-hmm.
they're not equal to each other.
I believe you. 48,000 over 120, you think is different than 240,000 over 600? I think you should double check that. I think you're wrong. Yep, it's like we'll check it, and like if I have a typo, I don't think I do. But as we're looking at these, not too bad. The math itself manageable.
Yeah.
Okay, so if one person says, yeah, that makes me feel good, but I need to know the other 20. You do not have to broadcast it. I'm not asking you to say, I'm bad at math, Holloway. Look at me, everybody. I don't need that. What I want is thumbs up says I can do a problem like this on my own. Thumbs down says, uh-oh. And anywhere in between is fine with me. You don't have to broadcast it out. You can hold it close. I just need to see where you feel you are mathematically. Thumbs up is you're good. Thumbs down, not at all. Okay, so if and when we see problems like this, because we're going to have time to work on stuff today, if you're struggling, who might you be able to ask?
You.
Bet. Cool. All right. So a couple things. We do have an assignment today. We'll get to it in a second. We're going to look at a few little pieces, though. First and foremost, electrical transformer. They come in a lot of shapes and sizes. They obviously look like these big boxes, and down south they're like up on the poles. When you actually look at a transformer, here's one. Now, it's a metal ring instead, and there's a ton of coils on this thing. Okay, this is not going to be a 4-step up. Definitely not a times 4. Okay, that's fine. They come in, like, here's the type that we drew when we see the current and stuff that we're looking at. They can get bigger and bigger if they're in a power plant. And I'm going to look at small transformer for sale, just so we can look at, I don't really care how much they cost. They get big. They get big, 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 eventually. So, if we're just looking...
Is it? Can it be? Is that what's in the green box?
That is in those green boxes. So, here's a pretty big one. Yep, everything in here is super dangerous. So the transformers produce the voltage that winds up killing you, yeah. Now, other things that entirely up to you. There is a link to this. I don't have a lab built around it, but I just want to check out a few things. Okay, so right now, as I move this magnet, what happens with this compass?
It moves.
Nothing surprising, right? We know that happens. We saw this the other day with an electromagnet. Okay? If you want to get online and play around with this at home to make sense of stuff, I would encourage you to, but I just want to look at a few of them together. Okay, here I have a magnet. Cool. And here I have a small coil and a light bulb connected to it. What are those little blue dots within the coil?
Negative charges.
They're negative charges. They're electrons. Nice job, Klein. Okay, right now they're not moving. Do you agree with that? Now, are they going to be impacted by this magnet? Like, check it out. If I take this magnet and move it, and I get close enough, the electrons are close enough and strong enough that they're moving along with the moving magnet. What do you notice is happening with the light as I do it?
It's turning on and off.
Like, it's slowly on and off. Like, I'm giving it energy. We can make the magnet stronger, I think. And even just changing the strength of the magnet does it. Because that field is changing.
What if you were to put this outside on?
So if it's
So-
at 100, it's...
So I'm just making, that's just on the simulation. As I move this magnet, the light turns on, right? Because I'm moving a magnetic field. Okay, the question became, what if it's on the other side? Well, nothing. It's still moving a magnetic field. It still works. Okay. I can move the magnet to make that electricity. What else could I move?
The light.
Like, it seems like unnecessary, but absolutely I can probably pick up this coil. I can wiggle it around and I can see that it's lighting up because it's moving through a magnetic field.
Oh my god.
But if it stops, the magnetic field is now just there. It's not moving anymore, which means the electrons don't move. There's no current being generated. Okay, let's go a step further. Here we have a coil with electricity running through it. Now, as we move electricity, if we just make this like less and less, so that's just changing the voltage, I want it to be 0. What do you notice about the magnetic field when there's no voltage, i.e. no current moving?
There's
No, it just...
The second I turn it up, though, what do you magically see happen?
Oh.
So it's...
It generates a magnetic field, right? So a current generates a magnetic field. The higher the voltage, the higher the current. Okay, I'm just pushing it through faster. There's a field being generated. We can see it. All right, what is this thing?
Transformer?
Is that a transformer?
Or a light bulb.
Wait, what?
Interesting. Okay, I actually have two things here. Right here I have a coil and currents running through it. What does that make happen? What generates around it as there's current? It's a magnetic field. This first one that we did, we had a magnet. Sorry. What? Didn't I have a light on one of them?
That one. Press that one.
Okay. When I have a magnet, if the field's changing, it generates electricity that generates that light, right? Okay, this one, if we look again, this is a magnet. This is an electromagnet. We made these the other day. As this moves in one direction, is the field changing at all?
Can you put it through the?
Can you put that one through the other one?
So I will, but before I do that, we're just going to let it wiggle a little bit. As I move the field around, I now have a changing magnetic field. What's happening when I have that changing magnetic field near this light setup? It turns it on. I can pass it through for sure. But if it's not moving and the field doesn't change, what happens with the light?
So it needs to move.
You have to have a changing magnetic field. Now, when I say moving, I can mean like if this is north, moving is this as well. This is still moving even though it's in the same spot. That is a moving field. Okay, if I move the magnet, just like we saw before, it generates current. If I move this around the magnet, is there still a moving magnetic field, essentially?
Yeah.
Like something else is moving, but there's still change because the angle that I'm approaching it changes. All right, put all these pieces together. So this is water. It's a weird analogy that they use. It's like my voltage, right? So the pressure that's pushing it through. When I turn this on, what's that magnet going to do? And as it spins, is it going to change the magnetic field?
Yes.
It better, right? The north and south are moving. It's going to make those things twist around. And by those, I mean these north and south indicators. When this water turns on, this magnet starts to spin, and this field everywhere starts to change, right? Is this living within the magnetic field right now?
No.
I mean, I think so, right? I can see the field here. It's not as strong. Why isn't this light on right now?
Because it's not moving.
The magnetic field isn't doing what?
Moving.
Moving. It's not changing. When I turn this on and this starts to spin, will that change the field?
Yes.
And by changing the field, what do you think it's going to do? We have a generator now where I have a spinning magnet that it's by water in this case, which is a super weird choice, but the same thing could happen by alternating current. This is all those ideas that we've played with throughout this section, this chapter, everything except the transformers covered right here. Cool. There's a link to this online. If it goes slower, notice the field's changing less drastically, less fast, means the current inside is wiggling less fast, means lower current. Cool. There's a link to this on the Google Classroom if you want to play around with it, okay? No, but I can probably move this one. Nope, I can't move it. Yep, sorry. All right. I would encourage you to check it out. Like, it's nice to just put these ideas together. For the next few minutes, what I would like you to work on is homework 7.3. Waiting for you on page 186. I want you to do problems 18 through 23. This, we have 15 minutes in class. I think we're finished, or we will finish. You will. What's up? Yes. Yes. Don't get it from the restroom.
And no card?